All right, so today we're going to continue on with the point group symmetry that we started last time. You know, we talked about the symmetry elements, and so remember those terms. Symmetry elements are the various operations that you do on a molecule. So it might be the identity operation, which is the do-nothing operator. You might wonder why we have an identity operator or do-nothing operator. It's the same as multiplying by 1. So all mathematical systems are going to have some form of multiply by 1, and this is really a mathematical system. All of those operations have a 3 by 3 matrix that you use to multiply by all the coordinates in a molecule. So think about the identity. If you have x, y, and z coordinate for an atom in space, and you multiply its x coordinate by 1 and its y coordinate by 1 and its z coordinate by 1, you haven't changed its location, and that's the identity matrix. So diagonals down this 3 by 3 matrix of 1, 1, 1, that would be the identity. But what if that z was a minus 1? So you multiply x by 1 and y by 1, but you multiply z by minus 1. You've just reflected it in the xy plane. All the z points have gone to minus z, and all the negative z points have gone to positive z, and you've reflected the molecule along the z-axis. There's an xy plane would be your mirror plane, and the z-axis coordinates would all switch places. And so that would be an example of a mathematical operation that is a reflection in the xy plane. So every one of those has a mathematical point associated with it, or mathematical 3 by 3 matrix. We could get into all of that, but I just sort of teach it visually. Okay. In graduate school, we'll get into the mathematical part of it. The inversion, it's just minus 1, minus 1, minus 1. You just invert all of the coordinates. So if it's up here in positive x, positive y, it goes exactly the same distance the other way to negative x and negative y. So that's why we have an identity operator, and then all those others. Rotation is not quite so easy, but it still has a mathematical association with it. And so those symmetry elements can be combined into groups of symmetry operations. So certain molecules have a symmetry associated with them, and so they will have those operations, those symmetry elements associated with certain molecules. And the more of those they have, the more symmetric the molecule is. Now, I'd like to point out this one strange word, this Schoenflies notation. That's the molecular point group label. And so we have, so when you hear that, when you hear me talk about Schoenflies notation, that's the point group label for a molecule, like a C2V or a C3V. That's the Schoenflies notation. So that's a vocabulary word for you. That's the label that we put on the different molecules to keep track of their symmetry. Now we can go through that flow chart, but let's do a quick Kahoot just to test your knowledge on the symmetry elements. So this will test your knowledge, and it'll also serve as a review if you're struggling to remember those things. Okay. To refresh. It's having me log in. I was logged in upstairs, but I guess I'm not logged in here. Okay, let's try that link again now. So the game pin is 258-2813. 258-2813. Let me switch over to the browser here, just a second. Okay. And There we go. $32, that's about right. Okay. Raise your hand if you want me to wait. Seeing none, let's get started. Okay, so just a short quiz on the symmetry elements. How far does a C4 rotation element rotate the molecule? So a C4 axis, how far does it rotate the molecule? Okay, so it's 90 degrees. You take that, whatever, 360 degrees, and you divide by that little number. So you're dividing the full rotation by 4. So 1/4 of a turn is 90 degrees. Okay. A molecule must have a central atom to have an inversion center. True or false? Okay, it's a little better than 50-50. Okay, the most classic molecule to think about is benzene. So benzene has an inversion center, but there's no central atom. So it does not have to have a central atom to have an inversion center. And so that's one way to think about these questions, is if you can think of an example molecule. And this will come as you work with symmetry more. You'll have example molecules in your head, like benzene, to say, I know benzene has an inversion center, I know it does not have a central atom, and so I know I'm confident about that question. The point group for water. Now, we haven't really talked much about point groups, so this is a stretch. You may be guessing, and that's fine. This is what we call a blind Kahoot. You take the Kahoot before you learn the material, and it gets it sort of primed in your head. Oh, wow, look at that. So the stuff we covered, y'all did terrible. And the stuff we haven't covered, you're doing great. Maybe I should quit teaching. Just let you learn it. There we go. Get out of the way. Y'all are funny. All right, question 4. The point group for methane is, I'm not going to say anything. I just seem to be hindering you. It's not the same without the music. I don't know why I can't get the music to play. Oh, wow. Okay, so methane, and this is one of those molecules you definitely have to have in your head. It's a classic tetrahedral molecule. So TD stands for tetrahedral in the point groups. So the Schoenflies notation for methane tetrahedral is TD. Yeah. So that's one that definitely would be in your head from now on forever, is that methane is tetrahedral. Yeah. And it's got those 4 electron domains, and each one has an atom on it, has the same atom. So we're good. 5 out of 5. The point group for the human body, there's no way you're going to get this one. I'll just say right now. Okay. The only thing that you can really think about the human body is that it has a mirror plane. And so this point group has an identity element and a mirror plane, and that's it. So without doing the flowchart, you're not going to be able to do that. So we're going to learn how to use the flowchart to determine these, and sure enough, y'all show me up. That's really good. So I'm looking forward to this next bit with the flowchart. So great job. They need to speed this part up. And top score is, yay, good job. Okay. So let's talk about this Schoenflies notation. That's what those last few questions were about. For water, for methane, for human body, everything in nature is going to have some Schoenflies notation. There's one for everything, even the most asymmetric molecule. That most asymmetric thing in nature would have no symmetry at all, but it would still have the identity element. And so there is a point group with just one element. That's the C1. And that one is because it only has one element in it. So this is the thing that we're going to be using to determine the Schoenflies notation for molecules. We're going to go through this flowchart. And if you've never used a flowchart before, the diamonds are decision boxes. So you reach a diamond, you have a decision, it's a yes or no question, and then you take whichever path is a yes or no. It's kind of logical. Well, it is logical. And then you get to the next diamond and you make another decision, and finally you reach the end point, which is a square on here, which has the Schoenflies notation. So we go through this, like if we're dealing with CO2 over here, then we would come into this top decision and say, is the molecule linear? Simple thing to think about. If all the atoms are on a line, it's linear. It doesn't just ask if it's long. You can have a long molecule, but if there's any atoms off the axis, it's not linear. So is it linear? Yes, CO2 is linear. Does it have an inversion center? And so look at CO2, the oxygen. If this oxygen goes through the center of mass to the other side, there's another oxygen. And so yes, an inversion center exchanges those two oxygens. And so I would say yes, and so it's D infinity H. The D comes from the inversion center, and the infinity comes from the rotation axis. You could rotate it with 360 divided by infinity and still get the molecule back. And then H has a horizontal mirror plane. So this is the horizontal mirror plane. So you can reflect it up and down. And so sometimes the Schoenflies notation has some information in it. It's not just a label. For this molecule, like OCS, so oxygen, carbon, and sulfur, it's linear, but it does not have an inversion center. And so you would end up with this C infinity V. And so you can work your way through these various flowcharts. There's one on that SymOtter page, and so let's go there. So here's our the SymOtter page, and here's the Symmetry challenge. So you click the Symmetry challenge, and you have all of these molecules over here on the left, and you can work through this. This is a lot of what you're going to do in the lab this week, is work through these various molecules, and you'll actually get to make some of them in the lab. Here's carbon dioxide, what we just did. So you can move it around, and then over here are the questions. Does this molecule have an infinite rotation axis? You could say yes, and it's right along this axis. Does this molecule contain an inversion center? Yes. And so you have determined the point group to be D infinity H. So I don't know what check answers means. Okay. Oh, look, cool. You can show the inversion center, and you can play the inversion. So that's cool. That's a new feature. Okay. Let's look at cyclobutane. So here's a molecule. It's a little more complex. So do you see a rotation axis anywhere? Like we're looking right down one, C4 axis. But I don't see any C infinity axes. Really, the C infinity axis is asking if the molecule is linear. So in my flowchart, the first question was, is the molecule linear? In this SymOtter, it's asking if it has a C infinity axis. And so we would say no. Does it contain two or more unique C3 axes? I don't see any threefold symmetry in this molecule. There's fourfold symmetry, meaning it's like four things rotating around each other, or there's two, like you could rotate a C2 here. But I don't see any C3, so I'm going to say no. Select the highest order proper rotation axis, if there are any. And so we're looking at this molecule. We have a C2 axis here, where I could rotate the molecule 180 degrees. Let's turn it this way. I could rotate it 1/4 of a turn, or 4 times I would get the molecule back, right? So a C4 axis, that's what we're looking for. So when it says the highest order, we have a C4 and a C2. We're going to pick the C4. Okay, so we're going to say C4 and select it, okay? And then it's saying, are there 4 C2 axes perpendicular? So we're looking right down our C4 axis, and we want to look 90 degrees to that. Is that a C2 axis? Yes. Is that one So that's a second one, that's a third one, and that's a fourth one. And if I go any further, I'm actually looking down the other end of the first axis. So I have 4 C2s that are perpendicular to the C4. So this is the toughest question on the flowchart. First, you have to find a C4 axis or a high order axis, and then you have to look 90 degrees and count up how many of the C2s there are. So if you find 2 or 3, you know, if you got a C4 like this and I find 2 or 3, there's going to be 2 more. I mean, you're going to have 4 of them. So we say yes. Does the molecule contain a horizontal reflection plane? Okay, so the horizontal plane is 90 degrees to the C4 axis. So we put that C4 axis going up and down, and then does this have a reflection plane? Yes, it does, because these hydrogens on top have pairs below that they can reflect into. So we would say yes on the sigma H. You have determined the point group to be D4H. So we'll check our answers, and we can come up here. Yeah, these two are correct. Let's see the highest axis. The C4 axis is right there. So see, we were looking down that axis, and then we can play that one. So that's the rotation for the C4. And then we can show these C2s that go around. So we had 1, 2, 3, 4. If I kept counting, see, I'm looking at the other end of the first one. So it looks like if you walk around, you might find 8, but you just got to keep track. I've looked at that one, that one, that one, and that one. I've got 4 of those, and they're perpendicular to the C4. So that's why we said yes to that question. We could play some of those. Okay. Excellent. Then does this contain a horizontal reflection plane? So we can show that. That's the horizontal. See how it's 90 degrees to the C4? Okay. And then we can play that one. And that's just reflecting top to bottom on that molecule. So this SymOtter site is for you to practice and get good at identifying symmetry. Way down here is a simple molecule, water. That was one of our test questions. And so, you know, is it linear? No. Does it have a C infinity V axis? No. Okay, so then are there unique C3 axes? No. Does it have any rotation axis? Yeah, it does. It has a C2 axis, right? It can rotate like that. So we're going to select that. Does it have perpendicular C2s? No, there's no way to rotate the molecule this way and get, because the hydrogens would go back to the top, and there's no hydrogens on top of the molecule for the bottom ones to rotate into. So we say no to those. Does it contain a horizontal reflection plane? Well, remember the C2 axis is going up and down, so the reflection plane would have to be this way, and there's nothing above the molecule that could reflect down. So we say no to that one. So there's lots of no's on this one. Does it contain 2 vertical planes? So yeah, looking right there, left and right could reflect into each other. So that's a vertical plane. And even though the molecules are all in this plane, that's also a reflection plane. So if the molecule is planar at all, that's going to be a reflection plane. Basically, each half of the atoms are going to reflect into the other halves of the atoms. Okay. And so we say yes to that one. And so we've got C2V. So that was the point group for water, which you guys knew. It was amazing. Okay. We can check our answers and just look at those reflection planes. See, those are the 2 reflection planes. And we can play that. So, and then the rotation axis up here, you can show that that's the C2 axis coming out of the top. And we can play that. Yeah, so if you can identify those symmetry elements, when you walk through the flowchart, you use those symmetry elements to decide whether you're answering yes or no. So practice, practice, practice on the SymOtter site, and then you have practice this week in lab. Okay. And so I've shown examples in the notes of all of the different molecules in this flowchart. Again, my flowchart's slightly different than the SymOtter flowchart, but not substantially. So once you get more familiar with the different questions, you'll see that my questions and SimAutor's questions are essentially the same. Okay. Notice these three groups here use ethane. So I'm using ethane as an example for all three of these molecules. Here, ethane is eclipsed, so the hydrogens are on top of each other. Here, it's staggered or gauche, where they're in between each other. And here, they're not exactly in between each other, and they're not eclipsed. They're just rotated a little bit. And so that's where you have D3H for ethane eclipsed, D3D for them to be staggered, and then if they're just off a little bit, it's just D3. So those are examples of the D groups. And so again, just work with that flowchart. And now we'll see why we want to know the point group of the molecule. So here's back to our particle in a box wave functions. We determined the selection rules on a post-it note last time using even and odd. But now we could take this wave function through that flowchart, and there's really only one thing. There's one axis, right? And so it only has two symmetry elements. It has the identity, which everything has, and it has inversion. So we can invert that axis where the positive x goes to negative x. Since there's nothing off the axis, we wouldn't know if there's any rotation. We can't do rotation because it's not defined. And then we can't also do any reflections because those are not defined. But we could do an inversion. So the only two elements our particle in a box can have are inversion and identity. And there is a character table for that. It's the CI character table. So our particle in a box would have the symmetry CI. And the little lowercase I indicates inversion. So these are the two symmetry elements, E and I, for our molecule. And this will allow us to label our wave functions and our energies with these Mulliken notations. And so these right here are called Mulliken notations. We'll see that spelled out later. Okay. And so we have AG and AU. The G and the U stand for even and odd. So we learn a lot of German in this course. We have eigenvalues, eigenfunctions, eigen meaning same. G is gerade. Looks like gerade. Okay. And U is ungerade. What do you think that stands for? That stands for even and uneven. So now you know here's some German. Okay. And so this top row is the even row. It's the only even row because, again, the characters in front are +1, both of them. And then down here we have this -1, and that's what makes it uneven or odd. So all other rows are odd. Only the top row is even. And this has ramifications for our integrals, right? And so we have these wave functions times each other. We can multiply those Mulliken notations, the rows in this character table, and determine what the end result will be. So let's do that. Let's label these. We'll redo the work we did the other day, only instead of writing even and odd, we're going to write the Mulliken notations for these. So we're going to come over here, and for wave function 4, we have AU. And then for wave function 1, n equals 1, we have AG. And we don't know what this equals. I mean, we kind of do, but let's pretend we don't. The one thing we don't have is the symmetry, the Mulliken notation for light. And so there we go to the character table. And so we come down here to the character table for CI. So that means it's really important to get the Schoenflies notation correct for your molecule, because that tells you what character table to use. And then you come in here and you find X. For our system, we find X, and it's AU. So it's that easy. You just go to the character table, and it will tell you what the symmetry of X is. So this is AU here. That's not bad. Once you get the character table, then it has all of the information. Remember I said it was the Rosetta Stone. It told us what symbols to use. And then we can do the direct products. And so down here is a thing called the direct product table. Now, how do I know the difference between a character table and a direct product table? Just look at them. Okay, look at the direct product table. It has all these Mulliken notations and no characters. It doesn't have plus ones and minus ones. But the character table has the plus ones and minus ones. Okay, so character table has characters in it. The direct product table is just a table of products of all these Mulliken notations. And typically it's written in a lazy way. Now, only one half of the table is filled out. So you've got a blank here, but that blank is just redundant. It's AU. So the makers of the tables are lazy. Okay, and so they could fill out the whole table, but they don't. They just fill out the lower triangle or the upper triangle, and you're supposed to figure that out. Okay, I'm sorry. That's just, people are lazy, and scientists are people. There you go. So we can come up here and we can do our direct product. So we want to know the symmetry of a function that has AU symmetry times a function that has AG symmetry. We go to our direct product table, and we find AG times AU is right here. So if we were to look at the top and it was blank, we see AG and AU is blank, well, we just go to the other triangle and find the same square. So AG, where it crosses AU, that's going to be the result of the product of those two functions. So the product of two functions of AG and AU would give you AU. And so we can bring this AU down, and now we have another product. We have two AU functions. So AU times AU, we come over here to our table, and we find where those intersect, and it's AG. Okay, and we look at this. This is equal to top row. Therefore, it's not equal to 0. And this is an allowed transition. So that top row is the only row that's even, and an integral over all space of an even function is non-zero. Okay, so that means it's allowed by symmetry. We can do the other one a little quicker so we don't run out of time. So we go and find wave function 3. Here it's AG. We know X is AU, so that doesn't change. And we know that wave function 1 was AG. And we want to know if this integral is going to be equal to 0 or not. So using our direct product table, we look at the product of an AU function and an AG function, and that gives us AU. We bring the AG down. And then we have, again, a function of the product of a AG function and an AU function gives us AU. So this is the integral over all space of a function that is odd. And so we know that that's 0, therefore not allowed. And I'll say because it's not top row. I can't say, notice I'm saying top row, not AG, because not every character table has AG in the top row. Sometimes it's A, sometimes it's A prime. So whatever the top row is the even one. I can't just say AG, right? It could be A1. For water, it's A1. Okay, so we're talking top row or else. So that's, again, I solve these complicated problems, at least for the selection rules, using a post-it note size calculation using symmetry. Now what I've shown you here with the particle in a box with AUs and AGs is exactly the same thing you will do with other molecules. So it could be an enormous molecule, it could be benzene or DNA or whatever, and you can use the same exact skill once you identify the wave functions in the character table. So this is the character table that we're using, and here's some examples of the character tables that we have. So no matter what the character table is, that top row is even and all the other rows are odd. So after doing these direct products, if you get a result that is on any row other than the top row, then you end up with a 0 result, and you end up with a forbidden transition. So all of these The top row is even, everything else is odd. And you can see that in the characters. You see there's lots of -1s and things on all of these other rows. All of these contain -1 somewhere, okay, which is a characteristic of an odd function, and the top row is straight +1s all the way across. So no matter what I do to that molecule, if it's an orbital or a vibration or whatever, and I rotate it and I invert it and I do all of the symmetry elements to it, and the wave function is still symmetric, then it's totally symmetric and it's going to have a non-zero integral result. So that's where we're getting this. That's why we care about top row. So if it's an even function, the integral over all space is non-zero. And if it's an odd function, it doesn't matter how it's odd. If it's odd in any way, it's going to cancel out when we do these integrals. So let's talk a little bit more about the character table. So this is an example of a character table. This is for water. If you were to take water through that flow chart like we did, you see that it's a C2V molecule. And so that's the character table there, actually, just that blue part. And that's the Schoenflies notation for the point group up in the corner. So that's how you decide which character table to use. You look in the upper left-hand corner at all those different tables, and you'll have 4 or 5 pages of these things. And they're on Blackboard. You can download them to use them for the lab this week. And you find that table that has that Schoenflies notation. These things here on the left, the rows are labeled with what we call Mulliken notation. So I've talked about that already, but here it is spelled out. It's M-U-L-L-I-K-E-N, Mulliken notation. And they're also called irreducible representations. So notice there, this gets into a longer, more involved mathematical discussion, but these are essentially like unit vectors, if you want to think of it that way. They're orthogonal to each other. They're not the sum of other rows. We can make a reducible representation that is a sum of all of these irreducible representations, but that's one thing that we'll get into. If you take advanced inorganic, then you'll end up making a reducible representation and then breaking it down into the number of rows of each type of symmetry. And these things in the middle, the +1s and -1s, are the characters associated with each one of those irreducible representations. Now, the thing that you will use the most are these Mulliken notations. So you're going to use these, all of these, frequently. And you're going to use these things on the right. So these are the Cartesian and rotational basis functions. So this tells you what the symmetry of the z-axis is. In water, the z-axis has A1 symmetry, but the x-axis has B1 symmetry, and the y-axis has B2 symmetry. And then over here, I've labeled this Raman because these are the second order interactions. And you can think of these as the 2-photon scattering process, like a photon coming in on the x-axis and leaving on the y-axis. Think about that. If a photon's coming in and it's got an oscillating electric field on the x-axis, and it's leaving on the y-axis and it has an oscillating electric field, depending upon the phase of those two fields, they could be in phase, where the electrical field is positive in, say, the x and y direction, so you get a positive field, but you might get a field that cancels out and goes negative in the -x, positive y area. And so it's like these two fields are interacting with each other to create a particular pattern. And we'll see that pattern if you take the x and y axes. Let's do x and y. Let me erase that. Okay. Okay. What are the numbers up here if I multiply x times y? I have positive x times positive y. So I get a plus here. And over here, I'm on the negative x-axis. So if I take these numbers, negative x times a positive y, I get negative numbers. Down here, I have negative x numbers times negative y numbers, and so the results of those are going to be positive. And then over here, I have positive x numbers times negative y numbers, and so the results of those are going to be negative. Okay. And this pattern, plus minus, is a pattern that you see when you have a situation of x times y. And in the scattering process, the two photons can interact with the molecule to kind of give that plus minus pattern. Now, there are things in atoms that could interact with that. You ever see the dxy orbital? The dxy orbital looks like this. It's kind of hard to draw for me, but where you have a positive color, a positive color, and a negative color. And so that dxy orbital is going to be described by xy symmetry, which means it's going to be an A2 orbital. So these are the things that we can use the character table for. And so since Raman is a two-photon process, all of the second-order items will be ways that Raman can interact with our molecules and with our atoms. Notice the top row is the only thing with even symmetry, and so an integral over all space of a result in our integrand of these functions multiplied by each other will be non-zero, but also this one will be non-zero. Sometimes when you multiply functions times each other, you get sums and differences. Think about the trig substitution where you have sine x times sine y. You get the cosine plus or minus and then plus the cosine. Yeah, the differences inside the argument, but you have a sum of two cosines. One of those might be even, and one of those sums might be odd. And so sometimes you end up with the sum here. And as long as the sum contains A1, then it's non-zero. So that's why we say if the result contains the top row. Then the integral is not equal to 0. Okay? So if it contains the top row, it could have A1 plus A2 plus E, all these different things. But if A1 is one of those things and A1 is the top row, then it's not equal to 0. The integral over all space of any other function in that character table is going to be 0. And so this is just some more vocabulary. This character table is a compilation of all of the vector representations of the point group. And those vector representations are irreducible. In the character table, they're the rows in the character table. You could make a reducible sum of those, and you'll do that in advanced inorganic. Okay. This Mulliken notation, there are some rules associated with that. It's not that you'll have to come up with these letters. They're already given in the character table, but sometimes there's some good information that can be had if you understand where those letters come from or what they mean. So if the character under rotation is a +1, then we call that A, that is a label A. So, some of these have A's and B's, like in water. So A1 and A2, notice the characters under the C2 axis are positive, and then B1 and B2, the characters under that are negative. And so that's how we determine between an A and a B for Mulliken notation. You're not going to have to determine these, but I'm just kind of showing you some of the rules behind the Mulliken notation. Okay, two-dimensional rows are labeled E. So down here, we have, like in a D3, D character table, we have this E here. Now, I'm sorry, but I didn't come up with this. E is used 3 different ways already in this course. It's energy, yeah. In SHSU, we use a quantum number subscript, so En, like energy of quantum state n. All right, so context is important. And then here, E, on the same freaking table, E is a symmetry element. Where's my pen? E is a symmetry element, which is the identity, and E is also a row on the character table, a two-dimensional Mulliken notation. It's not my fault. Don't put in the evaluations. Dr. Williams uses E for too many things. Or if you do, I'll know you're joking. Because I didn't make this up. All right. This is just, again, science is messy. We pull things from different fields and different branches of chemistry and put it all together. And it really depends upon when people publish this work, the variables that they use that become accepted, then they get all put together. And sometimes you end up with this clash of everybody using the same letter for different things. And so, golly, we have 3 E's now, but it's just the way it is. Then 3-dimensional rows. So I haven't talked about what 2-dimensional rows mean. So notice under this E row, or on this E row, we have a 2 here. And it's whenever you have a couple of symmetry elements or basis sets that can't be separated. Let's go up here to C3V. This is a little easier one to see. So in threefold rotation, I don't know if you remember from physics. This is from mechanics. When you're determining moments of inertia, when you have something with threefold symmetry or higher, it's what we call a symmetric top. And the rotation around X is the same as rotation around Y. That's a really useful result because it's not obvious. If I have something that is like a triangle, let's take BF3, so a triangular molecule. Okay. That rotation around X would give me the same, inertia as rotation around Y. Because rotation around X, there's an F, around Y, there's an F, a fluorine atom on the axis, and I'm just swinging 2 fluorines around. And it seems to me that that might be a different moment of inertia than rotating around X, where I'm swinging a fluorine and for all 3 fluorines around an axis. But threefold symmetry and higher, those moments of inertia are the same. And so there's no mass difference, there's no inertia difference of spinning that molecule around the x-axis or the y-axis. They're going to have the same moment of inertia. That means also that they have the same symmetry. And so this is why X and Y, if you notice in this threefold character table, X and Y are on the same Mulliken notation. They have the same symmetry. Okay. There's some ramifications of that. One is the moments of inertia are the same. Another is that their wave functions are going to have the same energy. They're going to be doubly degenerate. So if it's an energy level with an E Mulliken notation, it's doubly degenerate. So there's 2 equal energies. Okay, one is the X energy, one is the Y energy. Down here, we don't have an example of 3-dimensional rows, but in methane, there's a T. X, Y, and Z are the same. And so 3-dimensional rows would give us a T label. Subscripts G and U are Gerada and Ungerada. So down here, whenever you have an inversion center, then you have Gerada and Ungerada. Okay. And notice that when inversion is positive, +1, +1, or +2, you have the G's. When it's -1, -1, or -2, you have the U's. And so Gerada and Ungerada is telling us how it behaves under inversion. All right, so that's it. Go practice those point groups on SymOtter and enjoy building molecules this week in lab, and the TA will tell you about the coordinate systems.